Hello, I'm solving the specimen paper for 2022 9701 chemistry paper 4. The syllabus changed from this year, so this is going to be important for your exam in May. So the first question is, what is meant by partition coefficient? So basically, it's the ratio of the concentrations of a solute in two immiscible solvents, right? Solutions that do not dissolve in each other or do not mix with each other, right? So that's you get 1 mark for that. The second mark is for saying that they are at equilibrium. So it's the ratio of the concentrations of a solute in two immiscible solvents. You get 1 mark at equilibrium because the extraction has already taken place, right? The ratio after extraction, this is the ratio of the concentrations of a solute in two immiscible solvents. All right, that's it. If you want the paper, you can find this after googling. If you Google 9701 specimen paper, you can find it at Cambridge's website. Okay, so for the next one, ammonia is soluble in both water and organic solvents. However, ammonia is polar, right? Why? Because it has an electronegative nitrogen atom which has a lone pair. Okay, so let's move on to the next part. An aqueous solution of ammonia is shaken with an aqueous solution of ammonia is shaken with um, the miscible organic solvent trichloromethane. The mixture is left to reach equilibrium. Samples are taken from each layer and titrated with dilute HCl. A 25 centimeter cube sample from the trichloromethane layer requires 13 cm cube of 0.1 mol per d cube HCl, and a 10 cm cube sample from the aqueous layer requires 12.5. So clearly, more ammonia is present. Okay, no, we're not sure because there's 25 cm cube of the trichloromethane, the non-polar layer. Okay, so calculate the partition coefficient of ammonia between trichloromethane and water. So sometimes they're not going to give you a formula for KPC. So you need to remember that the one that comes first in the statement, right? The one that comes first in the statement, since trichloromethane comes first, it's going to be the numerator and water is going to be the denominator. So Kpc is equal to concentration of ammonia in CHCl3, the trichloromethane layer, divided by the concentration in the water layer, aqueous NH3 basically. So we know that concentration is going to be, like, we need to find out the moles first, right? So ammonia is a monoacidic base and HCl is a mono basic acid. They're going to react in a 1:1 ratio, right? So it's basically HCl plus NaOH. This is the result of the titration. So the moles is going to be 2.25 divided by 1000. I mean 13 divided by 1000 into 0.1. So it's 13 divided by 1000 into 0.1, or just 13 into 0.1. Okay, and this is for the trichloromethane layer. What about the aqueous layer? It's 12.5 divided by 1000 into 0.1. Okay, and for concentration, you know that it's moles divided by volume, right? So you need to divide it by the volume. In the numerator, it will be divided by 25 cm cube, and in the denominator, it will be divided by 10 cm cube. Okay, so why didn't we write the 1000s, by the way? Because they get cancelled out in the numerator and denominator. That's why we did not write it. Okay, it was actually like this. This is the concentration of ammonia in the trichloromethane layer. So it was actually 13 by 1000, right, into 0.100, zero point 0.1 mole per dm cube divided by 25 cm cube, right, which is 25 divided by 1000. On the other hand, in the aqueous layer, it was 12.5 divided by 1000 into 0.100, since 12.5 cm cube of HCl was required, divided by 12.5, 10 divided by 1000. So as you can see, the 1000s get cancelled out, so they're not required. We directly write 13 into 0.1 by 25 divided by 12.5 into 0.1 by 10. Okay, so that's it. So if you do the math, you're going to get 0.416. That's the KPC. So let's look at the next one. We have butylamine, which is soluble in both water and organic solvents. Why is that? Butylamine actually has the ability to form hydrogen bonds since it has the NH2 group. It is soluble in both water and organic solvents. But hear me out, it has a butyl side chain, an alkyl group, which is quite big. Typically, when the alkyl group is as big as this, when there are 4 carbons, it tends to be a bit insoluble. Okay, so it tends to be insoluble. Now think about it. We need to compare the new value, like if we dissolve butylamine in both the solvents, suggest how the numerical value of KPC of butylamine between trichloromethane and water would compare to the value of KPC calculated in A2. So we just need to think about polarity. Polar solids dissolve in polar solvents. So think about ammonia, right? Think about ammonia and butylamine. Both have the ability to form hydrogen bonds, right? Both have the ability to form hydrogen bonds. It's just that ammonia is going to be better. Ammonia will be better at forming hydrogen bonds because it's smaller. Okay, it does not have this insoluble part. Okay, due to this section, solubility actually decreases. So remember, even if you have the ability to form hydrogen bonds, if you have a part that is actually insoluble in the aqueous solvent or the polar solvent, it's actually going to reduce your solubility. So let's compare the KPC with ammonia. Butylamine compared to ammonia will be more soluble in the organic solvent, basically in the trichloromethane layer. As a result, the KPC will be larger. So let's answer this. We should say that KPC will be larger for butylamine compared to ammonia. Why is that? Butylamine contains a hydrophobic or a non-polar chain, right? So it will be more soluble in the non-polar solvent than ammonia. So the wording is, this is the first point, the ratio would be larger. Why? Because butylamine, right, contains a hydrophobic chain or a non-polar chain, right? So butylamine is more soluble in the non-polar solvent compared to ammonia. Okay, so that's it. Both of them are soluble in the soluble more in the polar solvent, that is water, but it's just that ammonia is more soluble there, right? As a result, this ratio increases because more butylamine actually dissolves in the trichloromethane layer compared to water if we're comparing it to ammonia. Okay, so butanamide is much less basic than butylamine. So solubility has nothing to do with basicity. Okay, so why is butanamide much less basic than butylamine? So remember, the strength of a base is actually dependent on the availability of the lone pair. We know that nonstellar bases are proton acceptors. So the strength of a base is dependent on the availability of the lone pair. Butylamine is a stronger base. Why? Because the alkyl group has a positive inductive effect. It makes the electrons, the lone pair, more available. Or you could answer it in this way. like since they're asking us why is this less basic. So butanamide, right? It has a electron withdrawing oxygen or a carbonyl group, right? So the presence of the electron withdrawing oxygen means that the lone pair is not available to accept a proton, or the lone pair is less available. Okay. So the presence of the electron withdrawing oxygen means that, or leads to the lone pair being less available. It's your wish. You can write whichever you want. Okay. So this was an important question. Next, for number 2, we have entropy. So typically, how is the specimen paper made? If you guys want to know, like they take some questions from previous years and just add a few new ones. Okay. Like this is from March Feb 19, but they just repeated a question. Okay, so this is also from previous year. The feasibility of a chemical reaction depends on the standard Gibbs free energy. If Gibbs free energy is negative, then the reaction is feasible. So, stating explain whether the following processes will lead to an increase or decrease in entropy. Entropy is the measure of randomness of a system. So, if we react magnesium with HCl, acid plus metal is, it actually gives us a salt and hydrogen gas. Since a gas is produced from a solid and liquid, entropy should increase. Okay, that's the logic. Dissolving sodium solid potassium chloride in water. So if you dissolve the solid in water, it turns into aqueous ions, which are more disordered, right? So the solid lattice turns into a solution of free ions. So it increases. Entropy does increase. The condensing of water to form steam. So H2O gas actually turns into H2O liquid. Condensation reaction occurs, right? So steam turns into liquid, gas turns into liquid. So there is a decrease in the number of moles of gas. So entropy actually decreases. You can write either one. Let's go to the next one. Magnesium carbonate can be decomposed on heating. Calculate del G. So we know that del G is equal to del H minus T del S. So sometimes you won't be given del S. You need to find that out. So del S is actually equal to, del S system is actually equal to del S products minus del S reactants. On the product side, we have carbon dioxide and MgO. So 26.9 plus 214 minus 65.7. We're getting an answer of 175.2 joules per Kelvin per mole. But you need to convert it to kilojoule per mole. Okay, because del H is given in kilojoules. 117. So if we convert it, we're going to get 0.1752 kilojoule per Kelvin per mole. Now to find out del G, it's going to be del H minus T del S, right? Which is plus 117 minus 298 Kelvin. That's given in the QP. Into 0.01752. We're getting an answer of plus 64.8. So since del G is positive, the reaction is not feasible. But think about it. If you increase the temperature, what's going to happen? If you increase temp, the value of T del S increases. T del S becomes more positive, right? And as a result, compared to del H, so del G will become negative at higher temperatures. But now the reaction is not feasible. The next question is on KSP. So deduce the trend in solubility of group 2 carbonates down the group. As you can see, KSP is becoming smaller. Smaller KSP means that solubility decreases. Smaller KSP means solubility decreases. Smaller KSP means solubility decreases. So as we can see down the group, solubility of carbonates decreases. We can give the reasoning. The justification is KSP decreases. Write an equation to show the equilibrium for the solubility product of magnesium carbonate. It breaks down to form one Mg2 plus ion and one CO3 2 minus ion. Okay, and you need to show the state symbols to get full marks. Okay. So it's actually MgCO3 solid plus aqueous. This was optional. Is equal to, or it forms an equilibrium with Mg2 plus aqueous ions and carbonate 2 minus aqueous. With reference to your equation in D1, suggest what is observed when a few cm³ of concentrated Na2CO3s are added to a saturated solution of MgCO3. So what actually happens? The common ion effect occurs. Why though? So basically, group 1 carbonates are soluble, right? Group 1 carbonates are soluble. So hear me out. This is what happens. So the first equilibrium is MgCO3 Mg2 plus carbonate 2 minus, right? So on the other hand, this is the other equilibrium. When we add sodium carbonate to the solution, it completely dissolves to give this. It's a full dissociation. So this is the common ion between both of them, right? So if this increases by a long shot, what will happen? If this increases by a long shot, the equilibrium will shift to the right according to Le Chatelier's principle, right? As a result, um, the concentration of MgCO3, magnesium carbonate solid, will increase, and we'll see that a white precipitate appears. Why? Because the common ion effect occurs, or you can say that adding carbonate shifts the equilibrium to the left. Calculate the solubility of MgCO3 in water in grams per dm cube. Okay, so we need to find out the solubility. We have the Ksp given. It's 1 into 10 to the power minus 5. So we know that 1 into 10 power 5, like this is x, this is x, and this is also equal to x, this is also equal to x, because they all have the same molar ratio. So we can actually say that the Ksp is equal to x square, or x into x, right? So we can say that the Ksp is equal to x into x, or 1 into 10 power minus 5 is equal to x square. Alright, so x square is equal to 1 into 10 power minus 5, or x is equal to 3.16 into 10 power minus 3 mole per dm cube, since the unit was mole square dm to the power minus 6. Now we need to convert this to gram per dm cube. We know that moles equals to mass by mr, so mass is equal to moles into mr. So the mr of magnesium carbonate is 24.3 plus 12 plus 48, 84.3. So 84.3 into 1 into 10 power minus 5 is actually equal to, or I mean 3.16 into 10 power minus 3 is equal to 0.27 gram per dm cube. They answered to 2SF, but they would allow 3. Okay, it would be fine. They don't look at significant figures much in A2 chemistry. Let's go to the next one. Describe and explain the variation in thermal stabilities of the carbonates of group 2 elements. So for carbonates, nitrates, it's the same answer. You need to talk about these 4 points. The thermal stability increases down the group, or you could say that more energy is required down the group. Why is this? Because the ionic radius of the cation increases, or you could say that the charge density decreases. Why? Because charge remains constant, but size increases, right? As a result, less distortion or polarization of the anion. Less distortion of the anion occurs, okay? Or you could talk about the weakening of the bonds, but less polarization of the anion cloud occurs. What anion cloud exactly? The carbonate ion. If we're talking about this question, we're talking about the carbonate anion, okay? So for number 3, we have a reaction of ClO2, 2ClO2 plus F2. They're saying that the rate equation is KClO2 to the power 1 and F2 to the power 1. Okay, that's the logic. That means it's first order with respect to both of them. So what is meant by order of the reaction? So order of reaction is the power to which a concentration is raised in the rate equation. This is a very common question. You need to memorize this. For example, if rate is equal to KHCl to the power 2, this power is the order of the reaction, okay? Next. Use results for experiment 1 to calculate the rate constant for this reaction. So we know that rate is equal to K into ClO2 into F2. So 2.20 into 10 power minus 3 is equal to K into 0.010 into 0.060, right? K is equal to 3.7. And if you're thinking about the units, rate has a unit of mole per dm cube per second, okay? And ClO2 has a unit of mole per dm cube. Fluorine has the same unit. So we can get rid of these two, And at the end, we end up with mole to the power minus 1, dm to the power 3, second to the power minus 1 after reciprocal, right? Okay, so use the data in table 3.1 to calculate the initial rate of experiment 2. Initial rate of experiment 2. So think about it. What happened in reaction 2? The concentration was increased by a factor of 0.025 by 0.010, and since it's first order, we don't need to square or anything, so it's just 0.025 divided by 0.010 into 2.20 into 10 to the power minus 3. It's going to be 5.50 into 10 to the power minus 3. Now use the data in the table to calculate the concentration of ClO2 in experiment 3, chlorine dioxide, right? Okay, so think about it. What happened in reaction 3 actually? We decreased the concentration of fluorine, okay, and we don't know what we did to the concentration of ClO2, but it seems like rate has increased. So since this was decreased, this one over here, this one needed to be increased, right? For sure, but it's fine. We can just denote this as ClO2. So it's going to be concentration of ClO2 divided by 0.010 into 0.040 divided by 0.060 into 2.20 into 10 power minus 3 is equal to 7.04 into 10 power minus 3. This is typically how you do this math. Okay, so this ClO2 is unknown. If you solve this equation, you're going to get 0.048. That's your final answer. It's always going to be like this, okay? Always the one after divided by the one before, always. What is meant by the rate determining step? So it is the slowest step in a multi-step reaction. Okay. For example, in SN1 reactions, we have two steps. Okay. In nucleophilic substitution SN1, we have two steps, but the first step is slower. So that is the rate determining step. Okay. So the mechanism of the reaction between ClO2 and F2 has two steps. Suggest equations for this. So we had two options. This mark scheme. Even though we have two molecules of ClO2, doesn't mean we need to use them in the first equation, okay? Because it's the, like, in our rate equation we only have one ClO2, so only one will be used up in the first step, okay? That's what you need to know, because even though you have two, doesn't mean both of them will be used up in the first step. One may be used up in the second step. So it's either ClO2 plus F2 is equal to ClO2F2 followed by ClO2F2 reacting with the remaining ClO2 molecule to form our final product 2ClO2F. You had another option. You could also use one ClO2 and one F2 to form ClO2F plus a fluorine free radical. Then the free radical reacts with ClO2, the remaining ClO2, to give ClO2F. And in total, we have two molecules of ClO2F, right? Your end goal should be getting all the products and using up all the reagents. So what is the rate determining step? It's actually step 1. How and why? Because 1 mole of fluorine and 1 mole of ClO2 are reacting. Okay, so the number of reagents in the slow step of the reaction, the number of reagents in the slow step of the reaction actually determine their order in the rate equation. What is the effect of temperature on the rate of a reaction and the rate constant? So as temperature increases, rate increases, and thus the value of k increases. But they asked a different question in March of 22. What is the explanation for this? So when temperature increases, rate increases. Why? More molecules have more proportion, a greater proportion of molecules have energy greater than or equal to the activation energy. Okay. As a result, more successful collisions occur. Okay, so you need to mention that. But since they talked about the rate constant here, the answer was like this. So the next question is actually based on organic. So we have methyl benzene, which reacts with concentrated HNO3 and concentrated H2SO4 in the presence of heat 55 degrees Celsius to form an intermediate T, and then followed by 4-nitromethylbenzene. The methyl group is orthopara directing. Okay, so it either directs to the second or fourth position. So in our diagram, we see that it's on the fourth position. There was another isomer possible, that was the nitro group being directed to the second position. So that's our isomer. You could draw it either way, any one works. Okay, so next we have the formation of the electrophile in this nitration. It's going to be 2 moles of H2SO4 reacting with 1 mole of HNO3 to form the nitronium ion, the protonium ion, and 2 HSO4 minus bisulfide ions. Next, we were actually asked to describe the differences between the intermediate and actually the methyl benzene. So hear me out. What actually happens? Look at methyl benzene. The delocalized ring actually spreads over all 6 carbon atoms, right? However, here look, it spreads over 5 carbon atoms. That's one difference. And in methyl benzene, all the carbons are sp2 hybridized. All the carbons are sp2 hybridized. They all have bond angles of 120 degrees. But in the intermediate T, right, one carbon, this one over here, as you can see, it has 4 sigma bonds. So it is actually sp3 hybridized and it has a bond angle of 109.5 degree. What other difference do we have? The intermediate, right, it has 4 pi electrons actually, and methyl benzene has 6 pi electrons. Okay, 6 pi electrons. Remember that. Okay, so the delocalized system extends over 5 carbons in T. T has one sp3 carbon, which is 109.5 degrees. Or you could talk about the shape. It's tetrahedral, and there are only 4 pi electrons in T compared to 6 in methyl benzene. So let's talk about this synthesis process over here. This is a really important question. And from 2020 onwards, you will no longer be given the data booklet. Okay, so any information you'll need will be attached to this the question paper. The periodic table will be at the end. Okay. Okay, so for D, we have benzocaine, which is used as a local anesthetic. It can be synthesized from 4-nitromethylbenzene by the route shown in figure 4.2. So, what are the steps involved? Clearly, in the first step, nitrobenzene is being converted to a phenylamine. The nitro group is converted to a phenylamine group. This is reduction. It requires 10 plus concentrated HCl plus heat under reflux. What is the second step? It is basically a condensation reaction. We react an acyl chloride with the amine to form an amide. Okay, we form an amide, the CONH bond. Then in step 3, we are oxidizing the alkyl group, the methyl group, to form benzoic acid, right? Using acidified KMnO4, concentrated, hot concentrated KMnO4, acidified. Plus, yeah, that's it. And in the next step, we're hydrolyzing the amide bond to get the amine back again. And in the final step, we are actually reacting benzoic acid with ethanol to form an ester. That's benzocaine ultimately. So we are tasked to give the systematic name of compound W. So remember, always guys, carboxylic acid has the highest priority. So that will be carbon number 1. Okay, this is our carbon number 1. So 1, 2, 3, 4. The amine group is on the 4th carbon. So it's 4-amino benzoic acid. Okay. So the reagents and conditions for step 1 is 10 plus concentrated HCl plus heat. Okay. Then reagents for step 2, we need acyl chloride, right? And it does not require any heating or anything because the acyl chloride is already very reactive. By the way, if you're wondering whether you could use an alcohol or not, the answer is no. It's not strong enough to react with the amine that's attached to the benzene ring. Okay, you need to use an acyl chloride. Reagents and conditions for step 3 and 4. For step 3, we need hot KMnO4 basically, and heat under reflux. Hot acidified KMnO4 and heat under reflux. Okay, and for the last step, step 4, we're hydrolyzing the amide, right? So just use H plus aqueous plus heat for hydrolysis. So a sample of benzocaine was analyzed by carbon 13 NMR and proton 13 NMR spectroscopy. Predict the number of peaks in carbon 13 NMR for benzocaine. Okay, so for carbon 13 NMR, it's always about symmetry. Okay, so hear me out. This is how you do it. I've drawn benzocaine over here. Okay, this is benzocaine. We need to determine the number of peaks for carbon 30 NMR. So we need to look for unique carbon atoms. Okay, we need to look for unique carbon atoms. So there's nobody like this CH3, right? So I'm calling this carbon number 1. There's nobody like this CH2, so I'm calling this the peak number 2. There's nobody like this COO, I'm calling this peak 3. Now we're gonna draw the line of symmetry through this benzene ring. This one is unique, right? Nobody's like this, so this is environment 4. Now look at these two carbons. These are not unique, right? Why? If you look at the proximity to this carbon over here, the green carbon, it's the same. It's just one carbon apart. So both of these are actually mirror images of each other and they are symmetric about this midline. So that's actually environment 4. These two are environment 6 and the carbon at the end, this one, this is environment number 7. So we're getting 7 peaks, right? For carbon 30 NMR. 7 peaks. Okay, so let's go to the next question. This is a question on the proton NMR of benzocaine. So it was dissolved in CdCl3. This is called deuterated trichloromethane because we're using deuterium instead of hydrogen. Deuterated trichloromethane. And the proton NMR spectrum of this solution was recorded as shown in figure 4.3. So what is the function of CdCl3? It acts as a solvent. As you can see, guys, how many peaks are we seeing here? In total, there are actually 1, 2, 3, 4, 5 peaks. So do you see this small peak over here? This peak is actually the reference peak. It's due to TMS, tetramethylsilane. It's, if they ever ask you what is the function of this peak or what is the function of TMS, you're going to say it acts as a reference. And if they ever ask you what is the function of CdCl3, you're going to say it's the solvent. Okay, remember these questions. So let's start. How are you going to figure this out? So the best way to think about this is, like, you cannot use the axis of symmetry for proton NMR. You have to work things out manually. Okay, I'm going to show you how. So let's do this step by step. So basically, let's figure out the splitting patterns first. This is clearly a multiplet. This is clearly a singlet. This is clearly a quartet. And this is a triplet. The TMS peak will always be a singlet, by the way. So clearly the singlet. Okay, how many protons are here in the compound anyway? So this H3, CH3, this is environment 1. This CH2, this is environment 2. Now, this carbon has no hydrogen. So remember, always just remember this. In the case of proton NMR, in carbon 13 NMR we used symmetry, right, to figure it out. But in proton NMR it doesn't really matter where you are. If you're part of a benzene ring, right, you will be part of the same environment. All 4 of these are actually environment 3. Okay, all 4 of these are environment 3, and this one, the one attached to NH2, this is actually environment 4. So remember, if you're ever attached to NH2 COOH, right, or OH, you're defined as a labile proton. That means if you add heavy water to the compound, the peaks will disappear. And also one more thing, since these protons are actually attached to carbons with like they're attached to carbons with very electronegative atoms, or attached to, since they're attached to a very electronegative atom, basically it interferes with the absorption of the, basically the oxygen is very electronegative, right? So as a result the proton becomes de-shielded. So since the proton becomes de-shielded, right, since the proton becomes de-shielded, that's why the chemical shift is much higher comparatively. If you're ever connected to NH2 OH or OH or COH in general, you're gonna have a very high chemical shift. So at first let's fill up the splitting patterns, right? It's pretty straightforward. The one at 1.2 is a triplet, the one at 3.5 is a quartet, the one at 5.5 is a singlet. Two doublets mainly refers to a multiplet. Okay, it's fine, it doesn't really matter. Benzene rings basically off limits. They're always going to be multiplets basically. So now we need to figure out the environment of the proton. So the singlet is clearly okay. If you're attached to N COH OH, I basically told you guys that there will be very high chemical shift. And one other thing I forgot to tell you was that it's going to be a singlet basically. So this is basically the NH2. Okay, this is basically the NH2. And how many protons are responsible for this peak? Two, right? There are two protons in NH2. Let's go to the next one. If we zoom in here, right? So how do you figure out the splitting pattern? Basically, if we're considering this environment, our environment number one, you need to look at the number of protons on the adjacent carbon. So look at the adjacent carbon. There are two protons, right? So the splitting pattern is actually n plus 1, which is 2 plus 1, which is equal to 3. So for CH3, the splitting pattern will be 2 plus 1. It will actually be a triplet. So look at the triplet. It's at 1.1, right? So this environment is actually the alkyl group, right? And the number of protons responsible is actually 3. What about this CH2 over here? Look at this. Look at the adjacent carbon. How many protons does it have? It's 3, right? So 3 plus 1 is equal to 4. So we're getting a quartet. And hear me out, it's closer to the oxygen, right? So it's more de-shielded. That's why the chemical shift is much higher. So it makes sense. And due to this high chemical shift, you need to mention this. You need to mention why it's so high. So you need to say that it's an alkyl group next to an electronegative atom, or you need to say it's CH2O, and 2 protons are responsible for this peak, okay? Explain the splitting at 1.2. Why is it a triplet? Because the adjacent carbon has 2 protons attached to it. Pretty straightforward. Okay, moving on to question part D. So this is mainly azo dye production. So for azo dye, remember you need the diazonium salt. Okay, the only way to get that is from phenylamine. You basically need to react HNO2, right? Or the alternate option was you could react NaNO2, sodium nitrate, and HCl to form HNO2, and they don't want the conditions, but it's basically less than 10 degrees Celsius. So you could opt for 5 degrees Celsius or something, okay? Then you're gonna get this diazonium salt, right? This group, N triple bond N, and the plus will be at the nitrogen attached to the ring. This is called the diazonium salt. Now, what next? We want to produce the azo dye. So always remember, for azo dye production, if it's not mentioned, it will always, the diazonium salt will always bind to the carbon opposite to the phenol. That means over there, that carbon. Okay, it will always bind to the carbon opposite to the phenol. So, and you need to get rid of the triple bond. It will turn into a double bond, and this group I circled over here, this is the azo group. All right. Okay, let's move on. So what is meant by lattice enthalpy or energy? So it is the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. Really important. Do not say energy required. It's the enthalpy change, because energy will be released in doing so. Why is it an exothermic process? Because it's bond making. Do you guys understand? The lattice energy actually involves the formation of uh, you know an ionic bond. So let's go to the next one. It's actually a Born-Haber cycle where forming potassium oxide. Okay, so let's look at the Born-Haber cycle. We want to form potassium oxide. So what do we need? We need to atomize the potassium solid to gas. Then we need to form the potassium ion, the K plus ion. Then we need to atomize oxygen. That means break O2 into 1 mole of oxygen atoms, followed by the first electron affinity of oxygen, then the second electron affinity of oxygen to get the oxide ion, anion, right? And then there are two routes. You can either form potassium oxide using the elements in their standard states, which is enthalpy of formation, as you can see in the bottom, or you can use lattice enthalpy, like it's using gaseous ions, the formation of the ionic compound, right? So you need to just remember one thing, that there are 2 moles of potassium. So anything you do with potassium needs to be multiplied by 2. So it's going to be, the roots are enthalpy H atomization of potassium into 2 plus first ionization energy of potassium into 2 plus atomization of oxygen. Why only once? Because we're forming 1 mole of oxygen atoms, followed by the first electron affinity of oxygen, second electron affinity of oxygen, followed by the lattice enthalpy is equal to the enthalpy of formation. There are two routes. Either you can take the shorter route, which is more direct, or you can take the detour, but both of them will have the same displacement or same energy. And also remember, this ionization energy is always positive, right? But the first electron affinity is negative, while the second one, like first onwards, any other electron affinity is negative, is positive. Okay, only the first one is negative, remember that. So atomization of potassium, which is 89 into 2, plus ionization energy of potassium, which is plus 418 into 2. The second ionization energy was given just to trick you, you don't need to use that. Okay, then atomization of oxygen, which is 496 divided by 2, half the bond energy of oxygen. Okay, O double bond, followed by the first electron affinity of oxygen, which is minus 141 plus 798, followed by lattice enthalpy, which is unknown. Okay, is equal to the formation, standard enthalpy of formation of potassium oxide, which is minus 361. If you solve this, you're going to get minus 2280. Okay, I missed a 0 here. State how the lattice enthalpy of sodium oxide differs from potassium oxide. Basically, sodium lies above potassium in the group, right? They have the same charge, but sodium has a smaller size. That means sodium has a greater, charge density. So it can form stronger forces of attraction with the oxide anion, right? As a result, sodium oxide should have a more negative or more exothermic lattice enthalpy than potassium oxide. The reason being, sodium has smaller ionic radius, right? And the same charge. So it has a greater attraction between the ions. You need to mention this point, okay? Moving on to question number 6. It's a question on transition metals. What is a transition element? It is an element forming one or more stable ions with incomplete d orbitals. Really important, okay? A very common question. So NH3 acts as a monodentate ligand. So what is a monodentate ligand? It is a species, okay, um, that uses a lone pair of electrons to form one dative covalent bond to the central metal atom or ion. Okay, species that uses a lone pair to form one dative covalent bond with the central metal atom or ion, or you could say a species that forms one dative covalent bond with the central metal ion using a lone pair. What about a bidentate ligand? It's a species with two lone pairs of electrons that uses and forms two dative covalent bonds, right, with the central metal atom or ion. To be a polydentate ligand, you need to have more than two lone pairs at least, and you need to form more than two dative covalent bonds. Okay, so remember, silver, guys, it only forms linear complexes. It has a coordination number of 2. That's why it's going to be AgNH32 plus, and ammonia has no charge, so the net charge will be plus 1. Okay, so look at this chromium complex. It has 6 monodentate ligands, out of which 4 are the same and 2 are different. So when you have this combination, if you have 6 monodentate ligands, uh, you will show no isomerism. If you have this combination of 4 same and 2 different, you're going to show cis trans isomerism. What about optical? When will you show optical? If you have 3 bidentate ligands. And if you have 2 bidentate and 2 monodentate, you're going to show both optical and cis trans. Okay? So if you have 4 same and 2 different, you're going to show cis trans isomerism. How though? For the trans isomer, the chlorine atoms will be along one line, right? And the net dipole moment will be 0 actually. And for the trans isomer, any other arrangement except the chlorine atoms being in one line. Okay, that's literally it. So explain why these two complexes are colored and why they have different colors. Okay, this silver complex, oh, these two complexes, the cis and trans complex, they actually have different colors. Why is that? So mainly because So why do they have different colors? So why does the color actually arise? Mainly due to, you know that the d orbitals are degenerate at the beginning, right? They have the same energy level. So when ligands actually use their lone pairs to fill up the vacant d orbitals, the d orbitals actually split into two levels, higher and lower. So the now what happens actually is that the electrons in the lower energy levels, they can actually absorb visible photons of light, and in the process of doing so they're excited. So the color we see is actually complementary to the color that is absorbed. So something that absorbs red and green light will be blue in color because it's not absorbing blue light, okay, like copper 2 plus ions. So here we need to explain that why these have different colors, mainly because the gap between the splitting is different. So the d orbitals split into two levels, two different levels. And why do we see the color? The color seen is actually due to the absorption of light or visible light photons, light in the visible region. And how does this actually happen? Electrons are promoted by absorbing the photons, right? Visible in the visible region. Now the energy gap is actually different for two complexes. So different a different wavelength of light will be absorbed, right? So different color will be seen. That's the logic. Okay, so I was talking about this. Ethane 1,2 diamine. This is a bidentate ligand. Nickel forms a complex with three of these, right? Now, here's the thing. If you draw the mirror, you can see that these images are non-superimposable. What does that mean? That these complexes are actually, optical isomers of each other. So I drew it this way. This is fine. You could also draw it this way. This also works. It's totally fine. Okay, no worries. You're gonna get full marks. That's showing the mark scheme. It's okay. So explain why the amino groups in ethane 1,2 diamine allow the molecule to act as a Bronsted base. A Bronsted base is a proton acceptor. So why is it able to do it? Because nitrogen has a lone pair, so it can accept protons. It can form dative covalent bonds. So we are reacting ethane 1,2 diamine with an excess of HCl, as you can see. So since it's excess, right, we want both amine groups to act as proton acceptors, right? So both of them will turn into NH3 plus. And of course you need to show the chloride as well, Cl minus, okay? And remember, for repeat units you need to show dangling bonds, but if they say draw dipeptide or tripeptide, do not show dangling bonds, okay? So under certain conditions, ethane 1,2 diamine react with ethane dioic acid to form the polymer Z. So guys, I've drawn the monomers on the right hand side. This is ethane dioic acid, this is ethane 1,2 diamine. So we want to show two repeat units actually. So here's the thing. This one over here is one repeat unit. Look at this. This is the section for ethane dioic acid. This is the section for ethane 1,2 diamine. Okay, that's the logic, right? So that's one repeat unit. So if we continue it, it's gonna be two repeat units. And look at the dangling bonds, right? These are showing that it's a continuation. It doesn't end here. And this is a condensation polymer, by the way. Sometimes they'll ask you to draw the displayed, draw the function, the linkage fully displayed. So keep track of that, alright? So we need to draw a 3D XY orbital. This was in the Marshall paper as well. It needs to pass in between the X and Y orbitals, and it can penetrate the Z orbital. That's totally fine, okay? This is what it looks like, okay? You need to draw both lobes, okay? Some transition elements and their compounds behave as catalysts. If they ask you what are the common properties of transition elements, go for variable oxidation states, form colored compounds, have catalytic activity, okay? So some transition elements and their compounds behave as catalysts. Explain why they behave as catalysts. What actually allows them to behave like catalysts? Mainly, the reason is they have more than one stable oxidation state. Wise, and also the vacant d orbitals are, or their vacant orbitals are energetically accessible, or you can say that they can form dative covalent bond with ligands. This actually helps them, act as heterogeneous and homogeneous catalysts. So the reasons are they have more than one stable oxidation state, and they can form dative covalent bonds with ligands since these vacant orbitals are energetically accessible. That's the logic. So iron in the Haber process. What is the heterogeneous catalyst? The catalyst will be in a different phase or state compared to the reagents. So ammonia plus hydrogen, they're gases. Iron is a solid, right? That's why it's a heterogeneous catalyst. But the other two, they're homogeneous, examples of homogeneous catalysts. So guys, please memorize the second one. It's a very common question. We also found in the March of 22 paper, so it's really important. Okay, so part C, let's check this. So the electrode potentials from the table can be used to predict the reaction that takes place when two solutions are mixed. Write an equation for this reaction, the one between tin 2 plus and 4 plus and iron 2 plus and iron 3 plus. So guys, we don't even need this info, right? We need this tin 2 plus and 4 plus. So we need this one over here, and we need the iron 2 plus and iron 3 plus. We need this, okay? So here's the thing, there are three types of half cells, gas half cells, metal ion, and metal ion in two different oxidation states. Both of these are metal ion in two different oxidation states. So we need to use platinum electrodes, right? So the one with the high reduction potential will be reduced, while the one with the lower one will get oxidized. So the formula is high reduction potential minus lower reduction potential. So it's plus 0.77 minus 0.15, which is plus 0.62, which means that the reaction is feasible. And one more thing, iron 3 is going to be reduced to iron 2 plus, and tin is going to be oxidized to tin 4 plus from 2 plus, I mean. Also, to balance the number of electrons, tin takes 2, right? But iron takes 1. So to balance the number of electrons, you need to multiply the reaction of iron with 2, and the electrons get cancelled out. Okay, that's it. Now we're doing 7D. How many questions do we have, by the way? 8, right? We're almost at the end. So for 7D, hear me out. This is a bit important. The question deals with the stability constant. It actually tells us how stable. It's actually the equilibrium constant for the formation of a transition metal complex. That's the definition of K step. The higher the K step, the more stable the complex. Okay, so hear me out and focus. We need to know this, we need to understand properly. So hexaquarine ions are pale violet. They form a colorless complex with fluoride. Okay. It has a K step of 2 into 10 power 5. On the other hand, the violet complex also forms a deep red complex with thiocyanate ions. Okay. So as you can see, both the fluoride complex and the thiocyanate complex actually replace or exchange the water molecules in the violet complex. What does that mean? Both this colorless complex and this deep red complex, both of them are more stable than the violet complex, as seen using this value. Since it's greater than 1, right? Since it's greater than 1, since it's not 10 to the power minus anything, the one on the right is more stable. But which one is more stable? The colorless one, since it has a value of 10 to the power 5 compared to 10 to the power 3. So the most stable complex is the fluoride complex, the colorless one, followed by deep red, followed by violet. It's the least stable. So look at experiment 1. We are adding KSCN followed by a few drops of KF. Okay, so if we add KSCN to this, pale violet complex, it's gonna turn deep red. Okay, then if we add fluoride, it's gonna turn colorless. Why was this possible? Because the deep red was more stable than the violet one, and the colorless one was the most stable compared to those two, right? Because the K step of equation 1 is greater than the K step of equation 2. That's why this was possible. But look at experiment 2. We're adding the fluoride one first, so the violet one turns to colorless. Then we're adding the thiocyanate ions, but the solution will not turn to deep red. There will be no change. Why is that? Because it does not form a more stable complex, right? So you have to give the explanation, right, in any one of them, saying that the stability of equilibrium 1 is greater than equilibrium 2, or for saying that the stability of the violet the colorless complex is greater than the one for the deep red one. Okay, so it stays colorless. All right, so violet to colorless, then no change or stays colorless. So what type of reactions are occurring? Ligand exchange. Now we have a reaction, or when we dissolve iron 3 salts in water, an acidic solution forms, kind of like aluminium 3 plus in water. The same thing happens. So we need to find out the pH of a 0.25 mole per dm cube solution of iron 3 chloride. So look at this. I'll show you how to approach this sum. So if you dissolve FeCl3 in water, you're gonna get FeCl3 that dissolves to form Fe3 plus and 3 chloride. Now this completely dissolves, right? So if FeCl3 has a concentration of 0.25, iron 3 plus will also have a concentration of 0.25. Now look at this. What do we have given? The Ka of this equilibrium. So this Fe3 plus, right, it forms an equilibrium with water. Ka is equal to H plus and FeH2O5OH divided by FeH2O6, products divided by reactants. And you know, Ka except buffers, okay, in Ka always the numerators, the concentrations will be equal, so you can actually square it up always in Ka while calculating pH except buffers, okay. So Ka is equal to H plus whole square divided by 0.25. You can actually find out the H plus concentration. It's actually 0.25 into 8.9 into 10 power minus 4. So it's going to be root over answer. Now if you just apply minus log H plus minus log answer, you're going to get the answer of 1.8. Okay, the answer is 1.8. Remember that. Next, we are dealing with the last one, ibuprofen and paracetamol. These are pain relief drugs. So what functional groups are present in each molecule? So ibuprofen, it has a carboxylic acid group here and an arene ring, but that's not a functional group, okay. What about paracetamol? It has a phenol group, non-alcohol, and an amide, okay. So ibuprofen contains a chiral center and has 2 enantiomers. So this is a new addition to the syllabus, enantiomers. So when you have a chiral center, you exist as 2 optical isomers, right? So each of the optical isomers, each is called an enantiomer, okay. So what are the similarities between the 2 enantiomers actually? Mainly, they don't differ physically or chemically. They have identical physical and chemical properties, okay, like same melting point, boiling point. So what's the difference? The difference is in their ability to rotate plane polarized light. One rotates it clockwise while the other rotates it anti-clockwise. That's it. So explain what is meant by a racemic mixture. So a racemic mixture is a mixture containing equal amounts of each enantiomer. So for each chiral carbon we have 2 optical isomers, right? If we have equal amounts, that means equal moles of each enantiomer in the mixture, typically what was supposed to happen? If we had one of them, plane polarized light would rotate either clockwise or anti-clockwise. But if we have equal amounts of both of them in the mixture, what will happen? The net rotation, right? The net rotation will actually be 0 because it will cancel out clockwise plus anti-clockwise, since it's the same magnitude but in opposite directions. Suppose it was plus 12.4 and minus 12.4 clockwise anti-clockwise. The net result will be 0. So you might find this in the next exams, saying what happens to plane polarized light when it passes through a racemic mixture. The answer will be there will be a net rotation of 0. Paracetamol reacts separately with 2 reagents, LiLH4, which is a reducing agent, and an excess of bromine. So basically LiLH4 reduces the amide, okay, to form an amine. The amide CH3CONH, right? Due to LiLH4, it's going to turn into an amine CH3CH2NH OH here. This is it. This is a reduction reaction. And for the next one, bromine, like we know that the phenol and aniline, they actually activate the benzene ring. How? The lone pair of phenol or amine, aniline, N or O, takes part in the delocalization of the benzene ring, right? So the benzene ring becomes more electron rich. That means it becomes an easier site of attack for electrophiles. That's why it's better, easier for electrophilic substitution. So if like the presence, since the fourth position is occupied, we're just getting 2,6, right? Dibromo, phenol, and this amide compound, and it's gonna be white in color. It's a white precipitate basically. Okay. Okay, so we're the last question actually. Write an equation to show how AlCl3 generates the electrophile for the conversion of X into Y. This is basically Friedel-Crafts acylation. Okay, so how is it formed actually if you think about it? Mainly the acyl chloride CH3COCl reacts with AlCl3 to form CH3CO plus and AlCl4 minus. This is our electrophile. Okay, AlCl3 basically takes away the chlorine, the chloride from the acyl chloride. Now let's draw the mechanism. Okay, how does this occur? Check this. This is the beginning. I'm just going to copy the compound from the top. We had this compound. So the first step is the attack by the electrophile. The electrophile actually attacks the benzene ring. The electrophile attacks the benzene ring. Okay, that's the first step. But always remember, arrows need to be drawn. Even though the electrophile attacks the benzene ring, arrows always need to be drawn from the nucleophile to the electrophile. Okay, that is our first step. Understood? What's the next step? We're gonna get a hybrid compound, right? Remember we discussed this at the beginning of the question paper. We're gonna get a hybrid compound where the ring actually spans over 5 carbons rather than 6, and 1 carbon is actually sp3 hybridized, while the others are sp2 hybridized. Okay, so what happens now? Heterolytic fission occurs, and this hydrogen actually loses its electron to the ring. Now we get our final product, right? This is it. This is our final product. The ring is back again over all 6 carbons, and we get this. We get our final product, right? And think about it. The H plus that we used at the big, like the H plus that was sacrificed in the second step, is released. The hydrogen. How is AlCl3 regenerated? Basically, remember we had AlCl4 at the beginning of the production of the electrophile. This will actually react with the H plus to form AlCl3 and HCl as a byproduct. So that's it. So if you have any other questions, let me know. And if you want to see videos on organic chemistry, AS and A2 organic recaps, I'm going to link them at the end of the video. Okay, see ya.